Hello, everyone. Thanks for attending our presentation. So today, Hassan from Molex and I from Matter, we will talk about the thermal considerations on the OCP NIC 3.0. So Anna is another presenter or contribution to this presentation, but unfortunately, she won't be able to be here. She will join virtually. After that, I will pass to Hassan to talk about the technical overview and the model setup.
Thanks, Kian. So I'll start with giving a high-level technical overview to set the stage up for what we're going to be talking about in the next couple of slides. So similar to the industry-wide trend where we're basically seeing increasing data rates, accelerating data rates, which come with the thermal cost of making thermal management critical as well as challenging. Similar is the trend that we see with 400 gig per second NICs. With the advancement towards 400 gig per second NICs, we're essentially seeing an increase in per port speed from 200 gig to 400 gig. Now, the obvious and preferred choice for these applications is a passive DAC cable. But based on feedback that we've been getting in the work group, there's potential concerns regarding the serviceability of these DAC cables. And those concerns are regarding, due to the higher band radius and shorter length limit, that leads us to look towards the less preferred option of the higher power AOCs. Now, in terms of the existing infrastructure, it is perhaps not optimized to accommodate for those high power AOCs, which has led the work group to sort of question the viability of existing infrastructure. And based on the thermal analysis and studies that we've done over the last couple of months, we've actually seen that each and every degree Celsius has an impact on the conclusion. So what that does is it makes it a mandatory prerequisite for us to align on those boundary conditions so that at the end of the day, we are simulating something that is real and representative of a realistic scenario instead of something that is overly optimistic and overly conservative. Because as we talked about earlier, since each degree Celsius has an impact on the conclusion, it does have a likelihood, depending on the wrong set of boundary conditions, it can pollute the resulting conclusion that we have, especially as it relates to the viability. In terms of this presentation, we're going to be talking about two NIC form factors. We're going to be looking at SFF, the small form factor, and the TSFF, which is the tall small form factor. Basically, the change towards the TSFF is the growth in the NIC faceplate by 2.7 millimeters, which allows for a higher NIC ASIC heatsink, as well as more space for the I/O cooling solution, as well as it allows the implementation of OSFP RHS. With that said, I'll start with the focus areas. So for the purpose of this presentation, as we mentioned earlier, we're going to be looking at the impact of TSFF versus SFF. In addition to that, we would also be looking at the NIC ASIC power limitations. So that is simulated only in the presence of DAC cable. So all that power is being pumped through the ASIC. Along with that, we are going to be looking at the type of module. We're going to be looking at the QSFP-DD Type 1 module, as well as the QSFP-DD Type 2A module, which basically has certain enhancements to the mechanical structure to enable better cooling. In addition to that, based on the collaboration that we've been doing within the work group, we very soon realized that there is different interpretation of the monitor points amongst different members, while the 70°C criteria is consistent. So we wanted to look at the impact of how the thermal results are going to change depending on the monitor point that we're going to be using. So for that, we're going to be looking at the mean top backshell temperature, the heatsink base temperature, and the nose temperature. In addition to that, we would also be looking at the impact of the type of testing fixture. So for that, we're going to be simulating with a single slot card, as well as testing it within the OCP thermal test fixture. And lastly, we would also be looking at the impact of cold aisle versus hot aisle, depending on the particular configuration of the NIC in the server. So going over the model setup, so for these set of simulations, we use the OCP NIC 3.0 card for both the TSFF as well as the SFF. In terms of the ASIC, we use the NVIDIA design for the ASIC, the ConnectX-XDX, with an ASIC power of 23 watts and a typical aluminum extrusion heatsink. So this is something that is not enhanced, optimized. It is just a relative heatsink that we're using for this study. For the QSFP-DD, we're using a multi-lane thermal model that represents an actual active optical module with a power of, I would say, a conservative power of 10.2 watts. And then again, for the heatsink, we're using something like a basic aluminum extrusion heatsink. So I do want to mention over here that all this study in the following slide is purely from a relative perspective. No heatsink solution, the I/O, as well as the ASIC heatsink solution has not been optimized. So the results in the next following slides are purely from a relative perspective. In terms of the simulation assumptions, we looked at both hot aisle and cold aisle. So hot aisle is basically when the NIC is placed at the rear end of the server, where it experiences the preheat, resulting in a higher ambient temperature as the NIC card sees. So we're looking at an ambient temperature typically of 55 degrees C with a slightly higher velocity range, ranging from 200 to 1,000 LFM. For the airflow direction, it's back to front for hot aisle applications. In addition to hot aisle application, we also look at the cold aisle applications where we are basically looking at a lower ambient because of the placement of the NIC in the front end of the server. So it experiences the cold, fresh air. And other than that, the velocity range, the typical velocity range that we are seeing for these applications is somewhere in the range of 200 to 600 LFM with an airflow direction of front to back. In addition to that, the text fixture that we are using for these applications is the OCP NIC 3.0 test fixture, which basically emulates how a NIC card, this sort of environment a NIC card would see in an actual server. It basically involves two identical cards, one placed on top of the other, where basically we're analyzing the bottom card for the thermal results, and the top card is just sort of a dummy card to emulate the airflow impedance and air bypass impact that you would see in those applications. Diving into the results, again, as we mentioned, we looked at the impact of the form factor. So based on this slide, we can see that when we move towards from the small form factor towards the tall small form factor, we do see a significant increase in thermal performance of the I/O, which is the QSFP-DD in this case, in terms of the mean top backshell temperature. And what's accounting for that increase or that improvement in thermal performance is basically that with the TSFF, now that we have the ability to have more room for the I/O heatsink solution, we are able to leverage that along with the fact that we are able to have better venting to have more airflow that is now being used for the I/O cooling. So again, we do see a bigger delta improvement for the TSFF, for the move towards TSFF versus SFF at lower airflows versus at higher airflows. The other variable that we investigated for this study was the comparison in aisle for the TSFF. So as we talked about earlier, for this study, we are going to be looking at both the hot aisle versus the cold aisle. So basically, based on the thermal results that we see right now, that 20 degrees C lower ambient that we have with the cold aisle basically translates very well to the I/O performance as well. So we can see almost a 20 degrees C reduction because of the lower ambient. So again, something that was expected, but we do see that the I/O running much cooler with the cold aisle applications. But again, we do have the caveat of limited airflow. So how much the actual performance is going to be, that is, again, to be determined for these specific applications. With that said, I'll hand it over to Yin to go over the rest of the portion for the study.
Thank you, Hassan.
Thanks.
So as Hassan just mentioned, in a NIC kind of design, we consider about the AOC cable, which is like a power dissipation on the QSP-DD module. And from this slide, we also want to see for another type of deployment in the data center is if we only have the dark cable, which do not have the power dissipation from the QSP-DD module. In another word, the power, the thermal performance will be more focused on the NIC ASIC only. So there are two plots showing in the both cold air and hot air with a TSFF factor and a SSF form factor, what will be the NIC ASIC temperature as a function of the inlet airflow. In overall, we do see because of the taller heatsink capability, the TSFF provides about 4 to 10 degrees C thermal benefit for the hot air side and 2 to 8 degrees C for the cold air side. The thermal performance gain gets more significant when the airflow is low. So again, also looking at the similar case, so we also want to present what will be the ASIC power limitation with different form factors. So in this case, if you look at the hot air side, so TSFF form factor provides about 2 to 3 watts more power capability on the NIC ASIC side, and the cold air side provides about 4 to 5 watts power increasement on the cold air side. So as Hassan mentioned, there is another focus area we want to we want to consider for the type of module. So in this case, in our analysis, we provided the results for the type 1 module and the type 2A module. So the type 1 QSP DD module has been widely available in the market, and the type 2A is an additional add-on to the specification, which is able to provide some more performance or some more benefit to the cable, which has an external integrated heatsink in the real part of the cable. As you can see from the analysis results, we do see about slightly less than 5 degrees C improvement from the type 2A module. So that means when we provide the thermal solution and analysis on the NIC thermal performance, we'd better to understand what is the cable module that we are using. Following that, we also want to discuss the monitoring location. So as you can see, there is a couple of locations we can monitor the temperature inside of the QSP DD module if it's assume it's an AOC and dissipate the power. So for example, we can monitor the heatsink base temperature, and we also can monitor the main top back shell temperature or the module nose temperature. So the definition of the heatsink base is the center point of the heatsink, and then main top back shell is just average temperature of the back shell temperature. And then also the nose area temperature is in the outside of the cage, but most close to the edge. So we define it as the nose temperature. So as you can see, the nose temperature definitely has a benefit because it's easier to apply the thermocouple and to measure the temperature without taking the module apart to glue the thermocouple on. So, but you also can see the different monitoring points have different temperature, and the difference can be very significant. For this specific case, we do see the heatsink base actually is about 5 degrees C lower compared with the module nose and the main top back shell. I also want to point out that normally we see the nose temperature should be lowest, and it's close to the ambient. But for this specific case, because we have the power profile and the power dissipation located in the nose area, that makes the nose temperature slightly higher in the normal cases. But again, for the purpose of this slide, we would to point out the monitoring location actually will be very sensitive. The temperature limitation will be very sensitive to what kind of monitoring location we need to use. And then last parameter we want to talk about is the test feature. In a normal thermal simulation environment, we tend to use a single slot model because it's easier to develop and easier to analyze with the lowest mesh requirement. However, it also has a limitation, it cannot really predict the bypass in the system and also the impedance from the system. So in this case, we compare the single slot system and the testing feature thermal modeling method. And we do see the temperature can be about 1 to 3 degrees C difference, but the difference gets smaller when the airflow gets pretty big. So in the early stage thermal analysis, we do recommend to use testing feature, which is more accurately represent the air bypass in real applications. Moving to the call to action slides, as you can see, all the focus areas or the parameters we just presented, it has a really significant impact to the overall thermal performance and the thermal design to the NIC. And we really want to get a consensus in our community, which will be a better monitoring location can reflect the real limitation on the QSP DD module. And also, we are looking forward to the active participation from the different vendors and the data center and the users and the system level to join our journey of the thermal analysis and tackle the thermal challenges on the NIC side. And as you can see from this analysis or study, we mainly focus on the QSP DD module, and we also want to get the comments from the community whether it's worth to expand it to the OCP iTrace or QSP DD AEC modules. And there are two links related to the NIC project wiki page and also the mailing list. We also encourage you to join the other NIC related talks. And also we have a demo in our expo hall. So Finally, thanks for attending our presentation, and truly appreciate if you have any questions and comments.
Thanks, Ian and Hassan. Yeah,
Thank
I
you.
think we can take one question. Okay, no, great, yeah. Thanks.
Thank you.
Thanks.